All right, so is this a context-free language? You said yes. What can we do?
Try to make a grammar for it.
Okay, we could try to make a grammar for it. Or we could describe a push-down automaton if we think that it's context-free. So did you try to make a grammar?
I have one.
Think you have one? What do you have?
S2, 0, S1. That's it. S2, 0, A1. And then A to either 1, A, 0, or just 1, 0.
Okay, so we could check this to see, does this grammar create that? So we can try to determine, do we create strings that just look like that? And if so, do we create all of the strings that look like that? What if we wanted to think about this from the perspective of a PDA? What would we do? What would a push-down automaton look like? Let's think what we could do. We could go through and push all the zeros onto the stack. So we have all the zeros on the stack. Then when you run into the first one, what do you do with it? Push all the ones on, right? So we push all the zeros, and then all the ones, doing this portion. And what happens if you run into, what happens as soon as you run into a zero then, after a one? We start popping ones. So here we're popping ones. And then when we run into a 1, we have to start popping zeros. If you don't pop the right thing, what does that mean? It means that you didn't have the right number of pieces. If you do pop the right things, and at the very end of the string, then the stack is also empty, then what does that mean? That would mean that we had the same number of zeros as ones on the outside, and the same number of ones as zeros on the inside portion. All right, so we can check to see if this grammar does this. We can check the PDA and see, does it really do what we wanted it to do? But conceptually, what is it? Push all these on, pop these, then pop these. But only pop them if you've read the right character. Okay? And so what happens? Is this language context-free? Yes, it is. We have a grammar or an automaton. And so the answer is yes. All right, let's look at language B. Excuse me. What about this language? Now the number of zeros is the same here, and the number of ones is the same there. all we've done is change the order of the pieces, right? But will the same approach work now?
No.
No, because we need to keep track of things here while we're using some of that and then other things here, right? Okay, so let's take a look at what happens. In this particular case, let's suppose that the language is context-free. Just pretend for a minute, right? So that means that any string that's long enough can be pumped, right? So that we would have these portions, you could make it longer or shorter. So let's pick a string that we know is going to be long enough. Remember we said that there's some length k that's the right length. So let's just pick our string let's just pick a string that we know for sure is long enough. We'll see if this works. I haven't thought through this example for a while. So let's just pick a string that might be long enough. I mean, it's definitely long enough for the k, but let's see if it works, if we can pump this. All right, so what's going to happen? We're going to be able to, so since the language is context-free, we can write this in this form, where the x part is non-empty, and where VWX is less than or equal to, the length is less than or equal to k. All right, so we would have Vx is non-empty, length of VWX is less than or equal to k. And then what would happen next is that u v to the I w x to the I y would be in this same form. Okay, so let's see what happens. VWX might include that first zero. If it does, what happens? Then the Vx part, if we pump it, say, up, that's going to affect these ones, how many of these there are, but not how many there are over here. So if the VWX part includes that first zero, we can't pump it up or down, because that will break this number of ones. All right, what if VWX is only in here? If it only is in this part of the first set of ones, pump it up or down, and again, it breaks the number of ones. What if the VWX part overlaps here? Again, it's going to break the number of ones. It can't include ones from, actually, it can't include ones from both pieces. This is probably a bad example. Because we could have something that overlaps there, where you pick up the same number of ones on this side and the same number of ones on this. Okay, bad example. Let's make it worse. let's do something like, make sure you put enough zeros in between to make sure that we can't overlap. All right, I apologize. Should have thought more carefully. Let's put a lot of gap between the zeros, or between the sets of ones. So now what happens? We can't have things from both of these parts or from both of these parts, right? So if we try to break this up and then pump, we're going to break somewhere where either not going to have the wrong number of zeros or the wrong number of ones in some place. Does that make sense? So what does this mean? This means that just changing the order here, this language is not a context-free language, but this language was. Sort of make sense?
Well, the idea is that it's still slightly confused, but the idea is that V and X are consistent.
They may not be the same value, but if you change the number of times one of them is created, then you've changed the amount of time that the other one has been created. So back here in this idea, the V and X portions might be different strings themselves, but every time you generate one of them, you generate a new copy of this, you generate a new copy of that. And what's happening in this particular case is as you change that, you're going to be either changing the number of zeros here or the number of zeros and ones here, but you're not changing things over there. Or you're changing the number of ones and zeros here, but you're not changing the ends. Or you're changing the number of ones and zeros here, but you're not changing the beginning. Or again, you could be individually changing the number of, I guess we could have just had k's, not even k plus 1. But you could be individually changing the number of zeros here, or just the number of ones, or the zeros, or the ones, but you can't pick up things from both places that you need to change. So they're spaced far enough apart so that there's no way to change both ones here or both zeros here in this pumping portion of the line. Make sense? Okay, so what happens, this context-free, this pumping lemma for context-free languages is like the old pumping lemma, only a little more complicated. But what happens, we know for sure that there's at least one language that a push-down automaton is not good enough for. So here's a language. Here's the language we just said. 0 to the I, 1 to the J, 2 to the I again, 1 to the J. What if we had 2 stacks? Can we do this with 2 stacks?
Potentially.
Let's see if we can describe what to do. We have stack 1. And we have stack 2. What can we do? As we read the zeros, we could push all the zeros on stack 1. And then push all the ones on stack 2. And then we start reading zeros again, pop from stack 1. What happens when we read a new 1? We want to pop the empty symbol from stack 1. Right? We want to make sure, okay, as I'm reading this 1, have I finished off the yeah, okay, we have the same number of zeros. But then at the same time, start popping from stack 2 and matching the ones in that case. Does that make sense? So if we had 2 stacks, we could keep track of the zeros and ones that are spaced apart, the separate issue here. But with 1 stack, we lose track. We can't keep track of this many pieces and this many pieces when they're separated by something. All right, but 2 stacks is that's not what we have, right? Well, actually, there's a thing called that. A 2 PDA is a PDA with 2 stacks. But it's not a context-free scenario, right? This is adding extra capabilities to our machine. So this is something more than context-free. What if we had a language like this? And again, all of these just being positive numbers. What do we know about the 1 stack scenario? We know 1 stack isn't going to work, right? You can't keep track of the A's over here and the A's way over there. Now, if we had K, J, I, we might be able to make that work. So what do you think? Can we do this with 2 stacks?
Probably do it with 3.
Well, so with 3 we could, right? Just keep track of each piece separately. So for sure with 3 stacks. But can we make this work with 2 stacks? Right, with 3 stacks, put the A's on stack 1, the B's on stack 2, C's on stack 3. And then when you get here, just start popping from stack 1, stack 2, stack 3. All right, so 3 stacks makes it easy. Can we do this with 2 stacks?
No.
Yeah, you could.
Tell me how.
If you pop,
We haven't pushed anything yet, so we can't.
no, yeah, if you push initially when you start, if you push A to 2 stacks, if you push A to stack 1 and stack 2,
Okay. So putting all the A's on both stacks.
and then on stack, when you get to the B's, you stack the B's on stack 1.
Okay. Oh, so you said stack 1. I'm sorry.
Yeah. And then the C's on stack 2.
But now we're here and we need to get to the A's, and they're underneath everything. So that won't work.
Oh, could you do, okay, instead you could do push all the A's onto stack 1, then push
Actually, push the A's on stack 1.
yep. Then push B's on stack 2,
Push the B's on stack 2.
and then push C's on stack 2. And then when you get to A's, you start popping the A's, but at the same time you're popping A's, you pop and push the C's to stack
No,
1.
because then you're getting A's and C's intermingled. You can't get to the A's that are underneath the C's.
Yeah. You pop all the A's. No, that's not either.
All right, what if we try something like this? What if we push all the A's on stack 1, push all the B's on stack 2. As soon as we see the first C, pop all the A's and push them onto stack 2. As soon as you run into the first C, you stop and you start popping A's until you get them all onto stack 2.
Yep, until you get empty.
right? And stack 1 is empty. And then we start pushing C's onto stack 1.
You should technically be able to do A, B, C.
Then we start popping A's from stack 2 until we run into a B, and then we hope that we pop a B, right? If we pop a B, we start popping B's. When we get a C, we check here, and you pop this to make sure it's empty, and then you start popping from here.
Okay, I knew it had to do something with shuffle.
We have to shuffle, right? We have to move things around, but can we do it with 2 stacks?
Yes,
We certainly can.
this is a little bit extra work.
A little extra work, but we can use the 2 stacks. We use them because we have to make sure things are in the right order on the stack. Make sense? But again, not context free, right? We have to have, and as far as the context free portion of the single stack, we don't have that. But then if we're trying to create a grammar for this, we would have to have, you can only do this at this time, and at other times you do this other thing. Right? At sometimes when you see an A, you put it on stack 1. Sometimes when you see an A, it's on stack 2. So that kind of idea. All right, what if we expand this language even further? Again, all of those being positive. Can we do that with 2 stacks?
You can do all of the ones in this format, but
What was it?
it's getting more complicated. But I think if all of these are like if you just did like 20 of them, I think you'd go to the right.
You think even with 20 of these, we could move things in the right way and move all these things to this stack, and and we could eventually have everything in the right order on the 2 stacks. And we just have to keep shuffling. It's a lot more work, but we can keep shuffling, and 2 stacks will always we can solve problems like this. We'll be able to recognize things that are in that pattern, right? That's what we mean by do this or solve this. Okay, but that's 2 stacks, that's not 1 stack. But we know for sure now that 2 stacks are way more powerful than 1 stack. We can do a lot of things that we couldn't do otherwise. All right, there's one more normal form that I want to talk about. This is going back to context-free grammars again, or context-free languages. This other normal form Greibach normal form. In Greibach normal form, everything is, all of the productions are of a form like this. So that means they're either a terminal followed by a collection of variables, none or one, right? None, one, or a bunch. But every production starts like this. What's the benefit of this normal form? Well, let's create an example, or let's look at an example of something that's not in that and convert it to that. And then we'll see what that can tell us. So these are capital. Right, so our terminals, characters are A and B, and then we have the variables S and C. So let's try to convert this